Welcome back, everybody, to another deep dive. And today we're going to be talking about something that I think is really interesting. It's actually called nuclear pasta.
Oh, wow.
And I know what you're
Yeah.
thinking. You're thinking like, oh, this is something that I can order, when I go to a fancy Italian restaurant.
Right. Yeah.
But unfortunately, no, this is something that is completely inedible. And it's something that is found deep in space.
That's right.
And this is going to be a really interesting deep dive because we're talking about the strongest material in the known universe.
Absolutely.
So without further ado, let's just dive right in.
Yeah.
So first of all, what is nuclear pasta?
So nuclear pasta is, as you said, the strongest material that we know of in the universe, and it's found in a very specific place, the crust of neutron stars.
Okay, so the crust of neutron stars. So
Hmm.
I think it makes sense to maybe take a step back and kind of explain what a neutron star is in the first place.
Yeah, absolutely. So neutron stars are these incredibly dense objects. They are the remnants of massive stars that have gone supernova. So when a star much more massive than our sun runs out of fuel, it can no longer support itself against gravity and it collapses. And this
Hmm.
collapse is so violent that it basically crushes the core of the star down to a tiny point.
Right.
And during this collapse, the protons and electrons in the atoms that make up the star, they get forced together and they combine to form neutrons.
Yeah.
So essentially you're left with this ball of almost pure neutrons that's incredibly dense.
Wow.
So dense that like a teaspoonful of neutron star material would weigh billions of tons on Earth.
Oh my gosh, that's unbelievable.
Yeah, it's crazy.
Okay, so we've got this like super dense ball of neutrons, but
Uh-huh.
I'm assuming that there's some kind of structure to this, right? It's not just like a uniform soup.
Yeah, that's a great point. So while the interior of a neutron star is mostly this uniform superfluid of neutrons as you move outward towards the surface, the pressure decreases slightly. And in this outer layer, which we call the crust, that's where things get really interesting. The neutrons aren't just randomly distributed anymore. They start to arrange themselves into these really weird and complex structures. And that's what we call nuclear pasta.
Okay, so this is where the pasta comes in.
Exactly.
So how did this pasta actually form?
So it's all about the interplay between two fundamental forces,
Oh.
the strong nuclear force, which holds the neutrons together, and the electromagnetic force.
Right.
Now, in the extreme conditions of a neutron star crust, these forces, they kind of compete with each other, and they create this energy landscape where the neutrons can clump together in a variety of different ways. And these different ways resemble different shapes of pasta, hence the name.
So I'm picturing like, different kinds of pasta, like spaghetti and lasagna. I mean, are those actual phases, or is that just kind of like a, cute name?
No, those are actual phases.
Yeah.
So we have the spaghetti phase where you have these long, thin strands of neutrons packed tightly together.
Right.
And then you have the lasagna phase where you have these flat sheets of neutrons that are layered on top of each other.
Wow, and I'm assuming that these different shapes, they have a big impact on the properties of the
Well,
material.
they do.
Yeah.
So for example, the spaghetti phase, it's incredibly strong. It's actually 1 billion times stronger than steel.
1 billion times stronger than steel. How is
Yeah.
that even possible?
It all comes down to the strong nuclear force.
Yeah.
So in these spaghetti strands, the neutrons are held together by this incredibly powerful force, and it takes an enormous amount of energy to break those bonds.
I mean, I can't even fathom how strong that must be.
Yeah.
If we could somehow like harness that strength here on Earth, I mean, the possibilities would be endless.
Oh, absolutely. But accessing and manipulating nuclear pasta, I mean, that's a challenge. That's light years away. I mean, it
Yeah.
only exists under these extreme conditions that we can't even replicate here on Earth.
So we've talked about the spaghetti phase. What about the lasagna phase? What's going on there?
So in the lasagna phase, the neutrons are arranged in these dense flat sheets. They're also incredibly strong, but they're even denser than the spaghetti strands.
Okay.
So imagine like stacked layers of neutron pancakes, but much, much harder than any pancake you've ever seen.
Wow. It's just mind-blowing to think that, something as seemingly simple as a neutron can form these complex structures just because of this crazy environment.
That's what's so cool about astrophysics, right? The universe is full of surprises.
Right.
And these extreme conditions, they lead to the formation of matter in ways that we could never imagine.
So we've got these different pasta phases. They're forming in the crust of a neutron star. I mean, what kind of impact do they actually have on the star itself?
That's a great question. And it's something that astrophysicists are still trying to figure out. But one of the key areas of interest is how these different pasta phases might influence neutron starquakes.
Neutron starquakes. So like earthquakes, but on a star.
Exactly. So neutron stars, they're not static objects. Their crusts can experience these sudden shifts and cracks similar to tectonic plates here on Earth. And these events, which we call starquakes, they release these enormous amounts of energy.
Really?
And we believe that the structure of the nuclear pasta in the crust, it plays a really important role in triggering and shaping these events. It's like you have this crust that's constantly, shifting and grinding, and all these incredibly strong pasta phases are interacting with each other. It's just a recipe for these amazing seismic events.
Yeah, wow, that's quite the image. But how do these star quakes, how do they actually, like, show themselves? I mean, can we actually see them from Earth?
We can actually observe them, and it's thought that neutron starquakes are actually responsible for some of the most energetic phenomena that we can see in the universe, like gamma ray bursts, for
Oh,
instance,
wow.
and also pulsar glitches.
Okay, wait, pulsars, those are those rapidly spinning neutron stars, right?
Yeah.
The ones that emit beams of radiation.
Exactly. And pulsar glitches are these sudden changes in how fast that pulsar is rotating. So imagine like a figure skater that's spinning and then suddenly speeds up or slows down. It's kind of like that.
And you're saying that these glitches, these sudden changes in speed, could be caused by nuclear pasta breaking and shifting in the crust?
That's one of the leading theories.
Yeah.
Yeah. It's thought that when that nuclear pasta rearranges itself, it can cause a change in the neutron star's moment of inertia, which then affects its rotation rate.
That's incredible. So we're talking about events that are happening billions of kilometers away on these objects that are so dense. A teaspoonful would weigh billions of tons, and we can detect them here on Earth just by observing tiny changes in the timing of pulses from a spinning star.
Yeah, it really speaks to the amazing precision of modern astronomy and just the ingenuity of scientists. We've got these incredibly sensitive instruments that can pick up on these tiny variations. And it's giving us this incredible window into what's happening inside these neutron stars.
Okay, so I have to ask this. If nuclear pasta is so unbelievably strong, how can it break at all? What could possibly fracture something that's a billion times stronger than steel?
That's a really great question. And it gets to the heart of why neutron stars are so fascinating. Even though nuclear pasta is incredibly strong, it's not invincible. The forces at play inside these stars are so extreme that even this super strong material can be pushed to its breaking point.
So what are these forces that can actually overcome the strength of the nuclear pasta?
Well, one of the key factors is just the sheer gravitational force. I mean, we're talking about objects that have a mass greater than our sun compressed into this tiny sphere. So the gravity is just immense, and it creates enormous stress on that crust.
So it's like squeezing a piece of pasta between two giant hands.
Yeah, that's a good analogy. The gravity is constantly trying to crush that neutron star. And nuclear pasta in the crust, it's pushing back, resisting that force. But even nuclear pasta has limits.
So the breaking of nuclear pasta is almost like a pressure release valve for the star.
In a way, yeah. It's how the crust adjusts to these incredible forces that are acting on it. And when it breaks, that energy that's released can be truly phenomenal. Like those gamma ray bursts and the pulsar glitches that we were talking about.
It's all so amazingly complex, but also incredibly fascinating. I'm starting to understand just how much is going on beneath the surface of these seemingly simple objects.
And we've only just scratched the surface. There's still so much we don't know about nuclear pasta and how it affects the way neutron stars change over time. Like, we're still trying to figure out how these different pasta phases affect the star's magnetic field,
Oh, okay.
and how the change from one phase to another might trigger all these different astrophysical events.
It sounds like we're really just at the beginning of understanding this amazing material.
Absolutely. Nuclear pasta is a pretty recent discovery,
Mm.
and it's opened up this whole new world of possibilities for astrophysical research. It's a reminder that the universe is full of surprises, and that the more we explore, the more we realize how much we still have to learn.
It's like peeling back the layers of an onion. And with each layer, we uncover more complexity and intrigue.
That's a great way to put it. Nuclear pasta is this window into the most extreme conditions in the universe, and it's pushing us to expand our understanding of physics and the very nature of matter itself.
So what's next for nuclear pasta research? What are some of the big questions that scientists are trying to answer?
Well, one of the main things is trying to actually observe nuclear pasta directly. We've been able to infer its existence based on how neutron stars behave, but actually seeing it, that would be a huge breakthrough.
But how can we possibly see something that's billions of kilometers away and buried deep inside the crust of a star?
It's a tough challenge for sure, but scientists are working on a lot of different approaches, from using gravitational wave observatories to try to detect the vibrations caused by starquakes, to analyzing the light emitted by neutron stars to look for any signs of nuclear pasta.
It's kind of like looking for a needle at a cosmic haystack.
It's even harder than that. But with all the advances in technology and the ingenuity of astrophysicists, I'm confident that we'll eventually be able to unlock the secrets of nuclear pasta and gain an even deeper understanding of these incredible objects.
This deep dive has been truly mind-blowing. I never would have guessed that something as seemingly simple as neutrons could form such complex and fascinating structures, let alone play such a crucial role in how neutron stars behave.
It's a testament to the power of extreme conditions to create phenomena that defy our everyday experience, and a reminder that the universe is a vast and wondrous place full of mysteries just waiting to be uncovered.
This whole conversation has given me a whole new appreciation for the complexity and the beauty of the cosmos.
Hmm.
Before we go any further, I think it's a good idea to just take a moment to recap what we've learned so far.
Sounds good. Yeah, we've covered a lot.
So we started by talking about the extreme conditions that exist in the crusts of neutron stars, where the intense gravity crushes matter into this sea of neutrons. And we learned how these neutrons can arrange themselves into these complex structures that we call nuclear pasta,
Uh-huh.
with phases that resemble spaghetti and lasagna,
Yeah.
each with its own unique properties.
Yeah, and we talked about how these phases, despite their incredible strength, they can break under the immense pressure inside the neutron star, and that leads to those starquakes that release vast amounts of energy. And we see them as gamma ray bursts and pulsar glitches.
Right. And we even touched on the efforts to try to directly observe nuclear pasta, which is a challenge that's going to require some big advances in technology and our understanding of the universe.
It's definitely a fascinating field of research, and one that's likely to bring many more surprises and insights in the years to come.
So before the break, we were talking about how nuclear pasta breaking can trigger these incredible events like starquakes and gamma ray bursts. It makes you wonder what other effects this bizarre material might have.
You're right. Besides those dramatic events, nuclear pasta also plays a more subtle role in how a neutron star cools down over time.
Cooling down. I thought neutron stars were incredibly hot, like billions of degrees.
They are at first. When a neutron star forms, it's incredibly hot, but over millions of years, they gradually cool down, and nuclear pasta actually plays a key role in that cooling process.
Okay, how does that work? How does nuclear pasta act like a cosmic radiator?
It's all about this tiny particle called the neutrino. You might have heard of them. They can pass through almost anything, even entire planets.
Yeah, I remember hearing that they're produced in nuclear reactions, like in the sun.
Exactly. And neutron stars, especially young ones, are full of neutrinos. They're created in the super dense core, and they need a way to escape. That's where nuclear pasta comes in.
So the pasta structure helps them get out. Is
Ah.
it like an escape tunnel?
It's more like a filter.
Huh.
The different phases of nuclear pasta, especially the lasagna phase, interact with neutrinos in unique ways. The lasagna sheets, with their dense, flat structure, they're really good at scattering and absorbing neutrinos.
So the neutrinos bounce around inside the pasta until they finally get out.
That's a simplified way to think about it. But yeah, essentially, this scattering process regulates the flow of neutrinos from the core to the crust and eventually out into space. And as those neutrinos escape, they carry away energy, which contributes to the cooling of the neutron star over time.
So the nuclear pasta is kind of like a giant cooling fin for the neutron star.
That's a great way to put it. It's not just a passive structure. It's actively involved in regulating the temperature and how the entire star evolves.
It's amazing to think that something we can barely comprehend, this bizarre nuclear pasta, plays such a crucial role in these cosmic processes. And to think it all started with a bunch of neutrons squeezed together under immense gravity.
It really shows how extreme conditions can lead to phenomena that we never expected and create matter in ways that we never anticipated.
This whole deep dive has been incredible. I'm going to look at pasta a whole new way from now on.
I can imagine. It's not every day you hear about a material that's a billion times stronger than steel, helps trigger starquakes, and cools down some of the hottest objects in the universe.
Well, that brings us to the end of our deep dive into nuclear pasta. We've explored its formation, its incredible strength, its role in starquakes, and even how it helps cool down neutron stars. It's been quite a journey.
It's been my pleasure talking about nuclear pasta with you. I hope you enjoyed this glimpse into the most extreme chemistry in the universe.
And who knows what other mysteries are hidden within this bizarre material. Maybe someday we'll figure out how to harness its strength, or even recreate it here on Earth. But for now, let's just appreciate the wonder of its existence and the insights it gives us into the truly mind-boggling nature of the cosmos. Until next time, keep exploring and never stop questioning.